This is Module 3, Lesson 3, Sampling Distributions for Proportions. In Lesson 2 of this module, we discovered sampling distributions for means. The only difference in this module, or in this lesson I should say, is that we're changing our interest here to proportions and away from means. We want to know how samples of proportions behave. Let's start with an example. Suppose that 1 out of every 4 students at CCBC has a tattoo. That would mean that our population proportion would be 0.25. We will denote a population proportion with a lowercase p. Here in our case, p is equal to 0.25. You can think of that as 25% of students have a tattoo. We're going to build a sampling distribution for a proportion. In other words, we're going to select samples of 40 CCBC students and compute a sample proportion for each of these samples. Now, a sample proportion will be a lowercase p, but it will have the added effect of having a caret on top, which I will call a hat. P hat is equal to the number of students in the sample that say they have a tattoo over the number in my sample. Let's work through a few samples. Here's my first sample. 40 students were asked this question, and if you count up the number of yeses among the 40, we find that 13 report having a tattoo. 13 divided by 40 is 0.325, a little higher than our population proportion. Sample 2, different 40 students asked about whether or not they have a tattoo. In this case, again, if we add up the number of yeses, we discover that 10 said yes, they have a tattoo. Our sample proportion, p hat, is equal to 0.25, the exact same as our population proportion. Sample 3, count up the yeses as we did in the last two. We discover that 7 said yes out of 40. This gives us a sample proportion of 0.175, a little smaller than our population proportion. Sample 4, 40 CCBC students randomly selected. We discover that 15 say yes, putting us at a sample proportion of 0.375. So what we see here is that our sample results vary from sample to sample. Sometimes they're a little lower than our population proportion, sometimes they're a little higher than our population proportion, and in some cases they're exactly equal to our population proportion. This is called sampling variability. Here are a few more samples that I did. As you can see, we don't consistently get the same number every sample. It varies a little bit. Sometimes it's below, and sometimes it's above our population proportion. A few more. Sometimes you may even have the same proportion show up twice, as we did with samples 13 and samples 14. If we continue this process, which I did, out to 200 different samples of size 40 students, notating in each of them how many reported yes, they have a tattoo, we could combine the results of all 200 samples and build something called our sampling distribution. Before we build it, let's remind ourselves, our population of CCBC students, we said 1 of 4 have a tattoo, roughly 25%. So this is our population. As you can see here, it's a categorical response, yes, no, to the survey question, and we had 25 say yes, and 75% say no, they do not have a tattoo. Now when we put all the results from the 200 samples together, and we plot them in a histogram, the histogram looks like this. How would you describe the shape of that histogram? Clearly it's unimodal. It's somewhat symmetric. It's not perfect, but it's a unimodal, somewhat symmetric distribution. You can see that most of the samples had a sample proportion that were somewhere around 0.25, our population proportion. So quite a few did that. With less frequency, you might have seen, or we will see, a sample proportion that's really small, back in like the 10%, 12% or so. And again, with less frequency, denoted by the shorter bars here, we would have a few samples that would have high proportion of students, much higher than our 0.25, reporting yes, they have a tattoo. But the majority of them are hovering around our population proportion of 0.25. Now with histograms, we often like to find the mean. I'll remind you that the mean is the balance point of the distribution. So if I were to place a little fulcrum underneath the balances, the fulcrum would occur or need to be placed just about here. The mean of this distribution, when calculated out from all 200 sample results, is 0.24913, which is approximately our population proportion of 0.25. This brings us to some formulas and ideas we can use with sampling distributions for a proportion. This picture here is just to remind you that the unimodal symmetric shape will show up if this is done. And also the p-hats are just to remind you that the distribution itself is made up of sample results from our different samples. The mean of this distribution, the center of it, underneath the peak, will be p, our population proportion. So sampling distributions will always center around the true population proportion p. The standard deviation, which will help us determine how skinny or wide this bell curve will be, can be determined by multiplying p times q over n and then taking the square root. Before we work our next example, we want to talk about a few assumptions we need to make in order to rely upon the bell curve showing up when we're working with sampling proportions or sampling distributions of proportions. The first thing we want to make sure is that our sample was a random sample, as well as the conditions for the binomial distribution are satisfied. That is, we have a two-sided outcome we're looking at, fixed number of trials, probability of success remaining constant, and things like that. Also, we want to make sure that there are at least 10 successes and 10 failures in the problem we're working. And you can check that by multiplying n times p and n times q and seeing they're both 10 or greater.